In this section of locational marginal pricing, we'll consider more general formulations of economic dispatch. We'll first look at decision variables, generator constraints, system constraints, and then define commodities. So previously we considered the case where there were two decision variables associated with each generator, power and spinning reserve. Now we're going to generalize. We're going to suppose that each generator K has multiple decision variables. For example, power, regulation, spinning reserve, and non-spinning reserve, and we'll collect them together into a vector xk that will be an element of R to the nk. In other words, it'll be an nk vector. For completeness, because there might be some variables in this more general formulation besides the generator decision variables, we'll collect them together into a new vector. Let me call it x np plus 1. It'll be the last vector of our full decision vector, the last subvector. For example, we might represent voltage angles or magnitudes in an AC power flow formulation, and we need some variables to represent that. In principle, there might be a cost associated with it, although generally that cost will be zero. We'll also sometimes want to represent a level of demand, and so we better define a decision variable for that. Let me call it x naught. In the simplest case, it's just one single entry, for example, the level of the scalar demand. In later chapters, in particular when we consider locational pricing, though, that vector might consist of the demand at all of the demand buses. In other words, it will be a vector with as many entries as there are demand buses. So let's collect all the decision variables of all of the generators and the other variables such as xnp plus 1 and the demand together into a vector x in Rn, where the length of n is the sum of all of those subvectors, x0 for the demand, x1 through xnp for the generators, and xnp plus 1 for the other variables. And we'll continue to use n sub p for the number of generators. So generator constraints. There'll be generator constraints, and we've previously represented them in the linear form. Delta underline k is less than gamma k times xk is less than or equal to delta overline k, where gamma k is a matrix and the deltas are vectors. In general, there might be multiple constraints. Rk, let's say, can generate pairs of upper and lower limit generator constraints. And of course, gamma k has to have as many columns as there are decision variables in xk. So paralleling our previous analysis, we've got a feasible set for the generator, S sub k. It's the set of xk's that satisfy the linear constraints. For demand, we could have a constraint of the form S0 is equal to the set of demands such that, say, 0 is less than the demand level is less than or equal to some desired or upper amount of demand. And we can put that in the form of our general set of linear constraints by defining delta underline 0 to be 0, the 0 vector, gamma 0 to be this a 1 by 1 matrix with the single entry 1, and delta overline 0 to be a 1 vector with the value d overline. Turning to system equality constraints, previously we considered where there was one equality constraint in the system constraints that was associated with supply-demand balance, and in particular balance of power, supply and demand. We're going to generalize the formulation. There can be multiple equality constraints. So in this case, we'll have a collection of equality constraints, Ax equals B, where A is an M by N matrix and B is an M vector. And previously, we've seen this idea before, we want to pick out the columns of AK associated with particular generators. So I'll define AK, it's a submatrix of A, it's an M by NK matrix, such that for K between 1 and NP, it's the columns of A associated with the decision variables representing generator K. For K equals 0, it's the columns of A associated with the decision variables for the demand. And for K equal NP plus 1, it's the columns of A associated with any other variables that we defined. There are also system inequality constraints. we considered previously reserve constraints, and we just had one of them, but we can generalize the formulation to the case where there's multiple such constraints. That'll be expressed in the form Cx less than or equal to D, and C is an R by N matrix, and D is a R vector, let's say. So as previously, we're going to define Ck to be the columns of C associated with decision variables representing generator K. K equals 0, it'll be the columns of C associated with the decision variables for demand, and for K equal N plus P, it'll be the columns of C associated with any other decision variables. Commodities. So in our basic formulation, there were generator decision variables Pk and Sk, and each of them appeared in system constraints. There were no other variables besides those generator decision variables. In our more general formulation, it could be the case that only some of the generator variables might appear in the system constraints, and furthermore, there might be some other variables besides the generator decision variables. Could be variable to represent the generator constraints, but didn't appear in the system constraints. And on the other hand, we might need to represent voltage angles, but these are not generator decision variables. So generator decision variables with non-zero coefficients that appear with non-zero coefficients in the corresponding entries of the system constraints are associated with commodities. Each row of A, each row of C defines a supply-demand balance or a minimum or maximum requirement for a commodity. And each row of A and C will be associated with a Lagrange multiplier, either a Lagrange multiplier on equality constraints or a Lagrange multiplier on inequality constraints that will price the associated commodities. So putting this all together, let's formulate our generalized economic dispatch problem. We're going to minimize over choices xk and sk, where k is 0 for demand, 1 through np for generators, and np plus 1 for any other variables. We're going to minimize our objective, f of x, generally the real power generation costs, subject to the system equality and inequality constraints. If we want to make the generator constraints explicit, then we could write that out by by explicitly showing those constraints as I've shown here. Notice that this is a very similar formulation to previously. We've changed our definitions of matrices and vectors, in fact generalized them compared to the previous formulation, but when we wrote down the first order necessary conditions, when we wrote down the pricing rule, we actually utilized exactly the more general notation that we're now going to fully exploit. In other words, this similar formulation is going to help us to understand the pricing rule for the generalized economic dispatch problem. As always, to get started, we're going to suppose that X star is a minimizer of our problem, in this case of the generalized economic dispatch problem. And because this problem is convex, we'll continue to assume that F is convex, and the linear equality and inequality constraints define a convex region. So the problem is convex. The first order necessary conditions are not only necessary, but sufficient. Here they are. This should look very familiar to the previous case. We've got the first line, which has got some gradient terms, some terms involving the system equality and inequality constraints, together with the corresponding Lagrange multipliers, lambda star and mu star, terms involving the generator upper and lower bound constraints, including the Lagrange multipliers, mu underline k, mu overline k on those constraints. The next three sets of rows are complementary slackness on system inequality constraints and generator constraints respectively. The next two constraints are the system equality and inequality constraints, then the generator inequality constraints, and finally the non-negativity constraints on Lagrange multipliers. So how do we turn that solution into offer-based economic dispatch? We come up with a pricing rule. Each generator, 1 through n, and the demand has decision variables xk. we're going to define a price for each entry in the decision vector that appears in the system constraint. And paralleling our previous development, let's consider a vector of prices pi xk that's defined as follows. Pi xk is equal to minus ak transpose times lambda star minus ck transpose times mu star. Let's consider a generator k equal 1 through np and demand k equals 0. Notice that profit maximization for each of these market participants is equivalent to the following minimization problem. Minimize xk and sk of fk of sk minus pi xk transpose minus xk. We'd like to minimize that. Each market participant would like to minimize their costs minus their revenues, or in the case of demand, we'll interpret it to be minimizing minus benefits plus their payments. Let's consider a maximizer of this profit maximization problem, also a minimizer of this minimization problem. And let's suppose that xk double star maximizes the profit. We can write down the first order necessary conditions. What we observe is that it looks very similar to corresponding conditions in the overall ISO problem. And effectively, the only significant difference is that here we've got lambda star, mu star, and the matrices and vectors that were incorporated into the ISO problem. So as previously, generator k equal 1 through np and demand k equals 0 will enforce its own generator or demand constraints. And as I mentioned a moment ago, the first order conditions for profit maximization reproduce the corresponding conditions in the first order conditions for generalized dispatch, so long as with some slight changes that just involve us setting the prices. In particular, if we set the prices as given by my definition here, we'll find that these conditions, as shown here, exactly reproduce the corresponding conditions in the first order necessary conditions for generalized economic dispatch. As previously, we can therefore find that xk double star, mu k double star, underline mu k overline double star, if we set them equal to the ISO solution, they'll satisfy the first order necessary conditions. So putting that together in a theorem, let lambda star and mu star be the Lagrange multipliers on the system equality and inequality constraints for our generalized offer-based economic dispatch problem. Let's extract Lagrange multipliers, those Lagrange multipliers, and calculate a price vector, pi xk. That's the price paid to generator k equal 1 through np. Let it be equal to minus ak transpose lambda star minus ck transpose mu star. Define the prices paid by the demand to be a naught transpose lambda star plus c naught transpose mu star. Then, if fk is strictly convex, we'll find that the values from the ISO give us the unique profit maximizing solution of the profit maximizing problem for generator k and demand 0, and the prices therefore strictly support economic dispatch. If fk is convex but not strictly convex, then there can be multiple maximizers, but xk double star equal to xk star. In other words, the ISO value is consistent. Choosing the ISO optimal dispatch xk star is consistent with individual profit maximization, and in this case the prices support but do not strictly support economic dispatch. In some cases, these Lagrange multipliers from the ISO problem may not be unique. There'd be multiple sets of prices that support economic dispatch. In this case, we might resort to some criterion such as fairness to choose particular values of the Lagrange multipliers. Let's see an example of this, and we'll illustrate it with respect to the first formulation of the spinning reserve constraint. So let's consider that formulation again. We met that first in section 8.12.1.4. In that formulation, we required that for each generator, there was sufficient spinning reserve being provided by the other generators to cover the outage of that generator. In other words, for each generator K, we required that the sum of the spinning reserve provided by generators J that were not K exceeded the generation provided by generator K. We can write that constraint in the form Cx less than or equal to D. We need to have a variable for a decision variable that includes the demand, the real power generations, and the spinning reserve. And if we define a matrix C that looks like this, its first column is all zeros, reflecting the fact that the spinning reserve constraint does not involve D, doesn't involve it directly. The second through NP plus 1th column is the identity matrix, and the last NP columns is a matrix that is mostly minus ones, except that it's 0 along the diagonal. The effect of this matrix when we multiply the kth row of this matrix into X is that we pick out P sub K and we subtract from it S sub J for all J's not equal to K. If we require that to be less than or equal to 0, then on rearranging, we've required that the sum over the J's not equal to K of Sj be greater than or equal to Pk. In other words, we've represented the first formulation of the spinning reserve constraint. As it happens, I can write those constraints more succinctly by observing that Ck, the columns of C associated with the variables Pk and Sk, that corresponds to generators 1 through NP, is I sub k and I sub k minus 1. I sub k is the column vector with 0 everywhere except for a 1 in the kth place, and 1 is a column vector of all 1s. So Ck has two vectors in it. The first one is zeros almost everywhere but a 1 in the kth spot, and another vector that's minus 1s almost everywhere but a 0 in the kth spot. Corresponding column for demand is just one column, and it's the 0 vector. Notice that in this problem there are as many system inequality constraints as generators, and we typically expect that only a few of them would actually be binding, perhaps only 1 or 2. If more than one of them is binding, then the Lagrange multipliers may be in fact non-unique. Let's suppose X star is a minimizer associated with Lagrange multipliers lambda star, mu underline star, mu overline star, k for each k. From the previous development, we now realize that the pricing rule for generator k, which would consist of a 2-vector of prices pk and sk, would be minus ak transpose lambda star minus ck transpose mu star. Well, ak is 1, 0. AK transpose is 1, 0. CK transpose is IK transpose, IK minus 1 transpose. Putting that together, that gives me a price for PK that's equal to lambda star, but we subtract off mu K star. Price for SK, however, is minus mu J summed over the J's not equal to K. In other words, it's the sum of the mu J's for J not equal to K. To understand that pricing rule, let's suppose that we have just one generator L that generates the most power, and furthermore, that the corresponding constraint, that the reserves that are covering PL is the only binding constraint. This is a special case, but it's a typical case. So in this case, by complementary slackness, mu L star is the only non-zero Lagrange multiplier. All but generator L, therefore, would be paid for energy at the price lambda star. Recall that the energy price in this case is lambda star minus mu k star. For the particular case of k equal L, that would be lambda star minus mu L star. For every other generator, it would be lambda star. In other words, every generator but generator L is going to be paid for energy at the price lambda star. And the total payment to all generators except generator L would be lambda star times the total production. All but generator L would be paid for reserves at the price mu L star. The payment for reserves is equal to the sum for generator K across J is not equal to K of mu J star. For every generator but generator L, this summation will be exactly equal to mu L star. For generator L, this summation will be exactly equal to 0. Therefore, all but generator L would be paid for reserves at the price mu L star, and therefore the total payment to all generators except generator L for reserves would be mu L star times the sum of a J not equal to L of Sj star. That would be mu L star times PL star. How about generator L? Remember that its price for energy is lambda star minus mu L star, so it would be paid lambda star in total, lambda star minus mu L star times PL star, but it receives no payment for spinning reserve. That means that the total payment to all generators would be payment for energy to all generators except L, the payment for reserves to all generators except L, the payment to generator L for energy, and the payment to generator L for reserves. If I collect together the first term and the first part of the third term, and I collect together the second term and the third part of this term, what I obtain is lambda star sum J not equal to L Pj star, then this and that, again regrouping gives me the lambda star times the sum of the generations, which is equal to the demand. That is to say, the total payment to all generators is exactly equal to the total payment by the demand at the price lambda star. Demand would pay at the price lambda star. This price would usually, but not always, be higher than the value obtained in our previous formulation of the other formulation of the reserves constraint. Total payment would be lambda star times D. This payment from the demand equals the payment to the generators. Notice that in this formulation there is no uplift. The energy payment exactly covers all of the energy, but also all of the reserves, with no additional uplift. And as a general observation, we'll formalize this in a moment, if spinning reserve, or for that matter any other ancillary services or any other system constraint, is explicitly represented as depending linearly on the generation power, then there's no uplift, since the total payment by demand equals the total payment to the generators. Let's see an example. It's the same example as before, but in this case we're going to accept that in this case we're going to change the spinning reserve constraint so that the spinning reserve has to be large enough to cover the largest single contingency. So the spinning reserve constraints are as we have discussed previously, most recently. It turns out that even with the changed spinning reserve constraints, the dispatch is the same as previously in the two respective cases. For D equals 300 megawatts, we want to generate 250 megawatts at generator 1. Of course, there's no reserves because that generator has no capability for reserves. Generator 2 should generate 50 megawatts since it is the next most expensive, next cheapest generator. It provides 60 megawatts of reserves. Generator 3 provides no production. It provides 190 megawatts of reserves. Generator 4 provides no power and no reserves. Lambda star is $17 per megawatt hour, and mu1 star, which is the Lagrange multiplier on the binding reserve constraint, is $0 per megawatt hour, and indeed all of the other Lagrange multipliers have value 0. The demand pays, all generation is paid, $17 per megawatt hour, and we have in fact the same price for energy as in the previous formulation of reserves. There's no separate payment by demand for spinning reserve. For D equals 500 megawatts, again we happen to have the same dispatch as previously, 250 megawatts from generator 1, no reserves, 170 megawatts of reserves from generator 2, 170 megawatts of power from generator 2, 60 megawatts of reserves from generator 2, 50 megawatts of power from generator 3, 190 megawatts of reserves from generator 3, 30 megawatts of power from generator 4, and again no reserves. It just turns out that lambda star in this case is the same as our previous formulation, although that may not be true in general. That is not true in general. And it turns out that mu1 star, the Lagrange multiplier on our first of 5 system inequality constraints, is $11 a megawatt hour, which is also the same as in the previous formulation. But all the other Lagrange multipliers on the 4 other system constraints have value 0 by complementary slackness. The demand would pay $28 a megawatt hour. All generators except generator 1 would be paid $28 a megawatt hour. But here's the difference. Generator 1 would not be paid $28 a megawatt hour. Instead, it would be paid lambda star minus mu1 star, or only 17. Notice that we have the same price for energy as in our previous sum of reserves is greater than a fixed amount formulation of reserves. And that is the same remuneration to all the generators except for generator 1. However, in this case, generator 1 receives a discounted energy payment, and unlike the previous fixed reserves formulation, there's no separate payment by demand in this case for spinning reserve. So, let me make some observations. Each pricing rule derives axiomatically directly from the formulation of the corresponding constraint. In our for all generators, the reserves has to cover the generation formulation of the spinning reserve constraint. If a particular constraint is binding for some generator L, then each additional unit of power produced by generator L that delivers energy to the system, that's a benefit, but it increases the amount of spinning reserve that must be procured. So intuitively, the price paid to generator L is reflecting not only the benefit of the energy, but rather the net benefit of the energy minus the cost of the increased spinning reserve that's necessitated by its increased generation. So when we change the formulation of spinning reserve, that could in principle involve different requirements for spinning reserve. And it wouldn't be surprising that if we change the requirements, we change the formulation, that results in a different dispatch, different requirements, would result in different prices. That's no surprising. The very interesting conclusion from this example, however, is that even if a change in the formulation doesn't change the dispatch, nevertheless the prices can change. The prices will reflect the incentives to behave consistently with optimal dispatch as defined by the constraints. So, you might ask yourself, why care about differences in prices if the dispatch doesn't change? Well, there's a good reason for this. Remember, we've discussed several times that the prices provide efficient incentives for both operation, but not only operation, also investment, at least at the margin in an incremental sense. Generator 1, which is providing the most power in the system and is therefore driving the amount of spinning reserve that must be procured, it should be paid less in principle than the base energy price, because a marginal increase in its generation capacity would necessitate increased spinning reserve. So that provides less value to the system than a marginal increase in the capacity of other generators, which would not require more spinning reserve. So the large generator 1 should only consider increasing its capacity if the amortized cost, amortized over the investment horizon and so forth, of increased capacity is less than that $17 per megawatt hour net benefit. If we pay the generator 28, we'd be paying it too much. We'd be encouraging it to expand even though the value of expansion would not be $28 a megawatt hour. So, formulation of constraints determines the pricing rule. And in practice, however, spinning reserve and other ancillary services are usually charged on something like a load-weighted average share of demand. So the equivalent total payment by demand to the fixed fraction formulation of the reserves constraint. Let's think about that. A load-weighted average sharing based on Lagrange multipliers would provide the correct incentive for ancillary services procurement and consumption for services that actually were required in proportion to demand. But for ancillary services that are not required in proportion to demand, load-weighted average shares are simply an uplift allocation mechanism. It achieves so-called revenue neutrality for the ISO. ISO doesn't take in any more money than it pays out. Such rules are typically motivated by fairness but have no particular claim to correctness. They typically do not provide the correct incentives for optimal operation and investment, as I've shown in the case of reserves and the large generator. And the implicit assumption is that the effect of uplift on energy prices doesn't distort consumption or generation investment decisions. So let's turn to uplift. A system constraint of the form sum of reserves is greater than a fixed amount, in other words, our fixed requirement necessitates an uplift. A system constraint of the form sum of reserves is greater than or equal to some fixed fraction of demand may result in the same net payment by demand but doesn't require an uplift. In that case, the main interpretation between the fixed fraction and the fixed reserves may be interpretation. But more generally, when we have system constraints of the form AX equals B, CX equals D, and B is not equal to 0 or D is not equal to 0, then those constraints will result in needing to charge an uplift, or conversely produce a surplus, whereas a system constraint that can be expressed in the form AX equals 0 or CX less than or equal to 0 doesn't require an uplift and doesn't produce a surplus. Let's make that formal. Let lambda star and mu star be the Lagrange multipliers on the system equality and inequality constraints for the generalized offer-based economic dispatch problem when we have demand represented explicitly as part of the decision vector. Let's define prices paid to the generators 1 through NP to be pi xk is equal to minus ak transpose lambda star minus ck transpose mu star. Furthermore, let's define prices paid by demand to be pi x0 equal to a naught transpose lambda star plus c naught transpose mu star. Then the uplift, or if it's negative, a surplus, is equal to minus b transpose lambda star minus d transpose mu. And furthermore, the uplift is 0 if b is equal to 0 and d is equal to 0. Let's see how to prove it. Well, the uplift is equal to the total payment to the generators minus the payment to the demand. So the payment to the generators is the sum k equals 0 to np of pi xk transpose xk star. The payment by demand is minus pi xk xk star, so I can incorporate the total payment to the generators minus the demand is simply the sum from k equals 0 to np of pi transpose xk. That gives me this term. If I now actually explicitly make my summation by summing up the rows of AK. Sorry, I can take the transpose, which gives me minus lambda transpose AK minus mu transpose CK, and now explicitly summing up these terms by summing up the corresponding AK times XK terms and CK times XK terms, I get minus lambda transpose A times X star minus mu transpose C times X star. Reassembling those entries into... So, just repeating, we've reassembled these entries into minus lambda star transpose A minus mu star transpose C X star, and collecting that together, we observe that because the equality constraint AX star is equal to B, requires AX star to be equal to B, and because the inequality constraint requires CX star to be less than or equal to D, we can observe that minus lambda star transpose AX star will be equal to minus lambda star transpose B, and furthermore, mu star transpose CX star will be equal to mu star transpose D by complementary slackness. Remember that by complementary slackness, mu star transpose CX minus D is equal to 0.